For the sake of vector calculus and integration, I have taken this topic, right? Wrote it as maths for fields and calculus. When we speak about this electromagnetic fields, we discuss something about the field quantities or the quantities in the region of influence of a particular source. Region of influence of a source is called as its field. Electric charge creates electric field. For us, current, and wherever you go, current creates magnetic field. Then in the electric field or magnetic field, we speak about flux, an imaginary quantity, and the potential, scalar potential in the case of electrostatic fields, and magnetic vector potential in the case of magnetic fields we discuss. Listen carefully. In electromagnetic fields, we generally speak about the quantities field intensity, basically a force, can be flux density, and potential. Listen carefully. When we define these quantities, step 1, the field quantity. Due to a point source. Here we introduce two things. In the case of electric field, point source is the point charge. In the case of magnetic field, point source is the current element. Point charge, or we call it as current element. First one is for electric field, next one is for the magnetic field. Point, infinitesimally small sphere, or the circle on a plane. In the space, it is sphere. Current element, it's infinitesimally small line, is the current element. Infinitesimally small, smaller than the smallest length you assume, it will have a length. Next. No source is the point source. When we charge an object to create a charge, it's an object with finite dimensions. It's distributed source. When you talk about the current element, I will pass the current through a surface or through a conductor. First, we define the field quantity due to a point source in the form of mathematical expression. Next, obtain the field due to distributed source. When we say that the source is distributed, this distributed source always contains uncountably infinitely many, right? Infinitely many point sources. Point source is infinitesimally small source. Every source that creates the field, irrespective of whether it is electric or magnetic field, in practice is distributed. When it is distributed, it will have infinitely many point sources. Contains infinitely many point source, ultimately forming a line or a surface or a volume. I will consider a line charge or surface charge or the volume charge. In the case of current, filamentary current we call it. Filamentary is what it says. Filamentary conductor is a normal conductor of circular cross section with radius tending to 0. Normally we cannot have it. But whenever we say that it is line, you should understand that it is a cylinder of 0 radius. There are cases where for us the current is there on a surface. We call it a sheet current. Especially at radio frequencies, the current through conductors normally becomes surface current. And at low frequencies, when you have a conductor of finite radius, current flows through the volume of the conductor, through the cross section of the conductor, maybe distributed uniformly throughout the radius or non-uniformly depending upon the frequency of operation. Obtain the field due to distributed source using integration. That integration can be a line integral, surface integral, or a volume integral. A line integral, surface integral, and a volume integral. Check it out. When you talk about line is a single integral. Surface is a double integral. Volume is a triple integral in any coordinate system for us. Listen. later on. We are supposed to understand the relation between these two in different cases through divergence theorem. Relation between these two integrals through curl and Stokes theorem. Gauss divergence theorem or Stokes theorem, where line integral is evaluated using surface integral. Surface integral is evaluated using volume integral. We'll see that. If you really want to understand these topics in mathematics through the subject that we can experience, it is electromagnetic fields through which we can really completely understand the importance and the relation between these integrals. Apart from that, in our syllabus, we have something called as gradient of and this gradient is used to relate the potential and the field quantity. Intensity. If you know the potential, easy to calculate. We use gradient to determine the field intensity. There we will understand actually the mathematical term like gradient, what it is. In mathematics textbooks, because it is there in the part of maths part of our syllabus. They will not be in a position to explain how these things have come, what is the importance of these things. They will only speak about what gradient is, what curl is, what divergence is. Apart from that, through curl only and Stokes theorem, we are going to talk about something called as Green's theorem. So in the calculus part, we are yet to discuss these integrals as line, surface, volume, or single, double, and triple integrals. And we want to see through subject where I get all these things. We'll in parallel do two things now. Electromagnetic fields, which is really required for us to understand the operation of different devices and this calculus, so that we can grow to the level of consolidating electromagnetic fields through this divergence, curl operations and all, using 4 Maxwell's equations through which we get into uniform plane wave and talk about the way in which two stations, one transmitter, another receiver are connected to communicate with each other through electromagnetic wave. We will extend it to another channels, free space or transmission line or waveguide is what we use as a channel. They are there in our syllabus. Please check it. This is what we are going to see. For this now, we need to know a part of geometry again. I'll just go back and then start revising the things. So integration we use here to get the expression for the field at a point because of a distributed source, knowing the field at a point because of a point source. So we are targeting many topics here. Only if you understand Green's theorem, we will be able to get into complex integration. While talking about complex integration, we will really see the Z transform in complex integration, right? The other part of Z transform we will see only as a part of complex integration. So whatever we are going to talk about from now, you please know that is extremely important for us to understand calculus, normal integration, and the vector calculus, gradient, divergence, curl, and Green's theorem. Right? Right. The gradient, divergence, curl, Gauss divergence theorem, Stokes theorem, and then Green's theorem. They are there in the syllabus part, and they're very important also for us. While doing so, we'll be talking about electromagnetic fields, which is the basis for all the devices as well as circuits, as well as the channels. Now, whatever is really important, I'll speak about it, right? Maybe we could have discussed it. Two-dimensional coordinate systems. Basically, two-dimensional coordinate systems are used to give the mathematical address, numerical address of each and every point in a plane by using a set of two numbers. You know that. In two-dimensional coordinate system, every point in a plane is represented as the point of intersection of two lines. Line 1 gives coordinate 1. And line 2 gives coordinate 2. And then we will keep them in the brackets and say C1, C2 is the coordinate of the point. In every coordinate system, there will be infinitely many lines. corresponding to C1, infinitely many lines corresponding to C2. Every point in a given plane is represented as the point of intersection of two lines. In this, in two-dimensional Cartesian coordinate system, first of all, we speak about two mutually perpendicular straight lines. Careful now. Two mutually perpendicular straight lines. There are infinitely many vertical lines in this system to talk about infinitely many points. And there are infinitely many horizontal lines in this system to talk about another coordinate. But what we do in this coordinate system is, I want to talk about the coordinates of this point. Then I will draw a line parallel to the first reference line, vertical line. This is parallel to this line. The distance of this is measured along this axis called as x-axis. This line intersects x-axis at x is equal to d. d1. d1. This is what we saw. Then draw a line parallel to the reference horizontal line. Measure the distance d2 between these two lines. And this is y-axis. This intersects y-axis at d2. On this line, wherever you go, because it is intersecting x-axis at d1, x is equal to d1. No, I forgot one more thing actually. For random variables also, when we talk about joint random variables, this is important because of which only I stopped it there. We are supposed to talk about joint distributions, conditional probability. So concentrate, because there are so many topics dependent on this. We saw this. X coordinate of any point on this line is d1. This is the line y is equal to d2. X is equal to 0 is y-axis. Correct? Y is equal to 0 is x-axis. And the coordinate of this point is d1, d2. It is the point of intersection of two mutually perpendicular lines. One parallel to y-axis, giving the x coordinate. Another parallel to x-axis, giving the y coordinate. Check it. You comfortable? This is what we discussed earlier also. Now check it. There are 2 points with coordinates x1, y1 and x2, y2, wherever they are. I wrote it in this order. The distance between these 2 points in this coordinate system can be calculated using Pythagoras theorem, where I represent this as the hypotenuse of a right angle triangle. Listen carefully. This is x is equal to x1 line. X is equal to x1. X is equal to x2. I want you to concentrate now. This side is x2 minus x1 modulus. Correct? You agree with this? X2 need not be there to the right only, wherever it goes. Right? This x2 minus x1. Or x1 difference of x2 modulus is the distance between these 2 points along x-axis, where y remains constant and x only changes. This is actually this point. What is the coordinate of this point? It is lying on x is equal to x2 line and y is equal to y1 line, right? This is x is equal to x1, x2. This is y is equal to y1, y is equal to y2. x2, y1. x1, y1 to x2, y1. There is only change in x without changing y. X is changing from x1 to x2. So, the distance traveled is mod of difference between the coordinates. In the same way, this is mod of difference between y coordinates, where this side is there on the line with x is equal to x2 from y is equal to y1 to y is equal to y2. Mod y1 minus y2. The distance between these 2 points now is x1 difference of x2 whole squared. We need not take modulus because anyway we are squaring it through Pythagoras theorem, plus y1 difference of y2 whole squared. Is the distance between the points x1 d is equal to this. Next, vector from x1, y1 to x2, y2. Careful now. Represented in the standard form. Standard so-called component form. Is what? Standard components are orthogonal components. In two-dimensional coordinate system, try to recollect. We define two standard unit vectors, namely Ax and Ay, I and J, normal, right? These are the notations. I cap, J cap, or Ax cap, Ay cap, I cap, J cap, they call it. Normally, we will be using small ax and small ay for standard unit vectors. At any point x comma y, please remember, you have two lines. X is equal to constant line. Y is equal to constant line passing through that point. X increases to the right. Y increases in the upward direction, correct? X increases to the right, normal. Y increases in the upward direction. What is Ax? At any point, vector of unit magnitude perpendicular to x is equal to constant line passing through that point in the direction of increase in x. Is Ax. Ay. Vector of unit magnitude perpendicular to y is equal to constant line passing through the point of interest xy in the direction of increase in y. Let me repeat the statement. Ax at any point is the vector of unit magnitude perpendicular to x is equal to constant line passing through that point in the direction of increasing x. Ay is the vector of unit magnitude. Its direction is fixed. Perpendicular to y is equal to constant line passing through the point of interest in the direction of increasing y. Because different line with different x is equal to constants are all parallel. You take any x is equal to constant C1 line. Any other x is equal to constant C2 line, both positive, both negative, one positive, one negative, right? Doesn't matter. All the lines are parallel to one another. Because of which, wherever you go, Ax will have the same direction to the right. wherever you go, since all y is equal to different constants lines are parallel, if unit vector is perpendicular to one line, it is perpendicular to every other line. You know that. Ax and Ay have fixed directions. Ax and Ay have fixed directions. Then, listen carefully. We want to talk about a general vector from x1 comma y1 to x2 comma y2, vector from point 1 to point 2. Every vector you know is associated with two things, right? One is magnitude, another is direction. This vector x1 y1 to x2 y2 is also called as the position vector of the point x2 y2 with respect to x1 y1. Whenever I want to add so many vectors in xy plane, I will add all their x components, get the x component of the resultant vector, and y component by adding all their y components. Because addition is performed component wise, one of the very useful mathematical representation of the vector is the resolved standard component form. In this, again, this is what we did. Please consider, I am talking about the vector from x1 y1 to x2 y2. This vector is represented as the linear combination of the vectors ax and ay. In which the first component is x component. Now, what is this now? x2 minus x1 ax. You know it, but it's my duty to tell. If x1 is 1, x2 is 5, I know that in x it is going from 1 to 5, means it is going in positive x direction. Ax is also in positive x direction. It will definitely be of 4 units. 1 to 5 is 4 ax. But if x1 is equal to 1 and x2 is equal to minus 4, then it is minus 5 units. I know that 1 to minus 4 it is going. I will get that this x2 minus x1, if it is positive, this x component is to the right. We know because we discussed it. If you multiply a vector with minus 1, its direction exactly reverses, keeping the magnitude same. Ax is the unit vector to the right. Ay is the unit vector to the left. Any vector is its unit vector multiplied by magnitude. If x2 minus x1 is positive, its magnitude is x2 minus x1 plus ax. If x2 minus x1 is negative, what is that I have to do? Minus ax into x1 minus s2, which is positive. Minus ax is the unit vector for me. Mod x1 minus x2 is its magnitude. If x2 minus x1 is positive, mod is x2 minus x1 only. If it is negative, mod is x1 minus x2. Minus of x2 minus x1 is its modulus. In the same way, because it is going mathematically from y1 to y2, the other component is y2 minus y1 ay. This vector is x2 minus x1 ax plus y2 minus y1 ay. This plus talks about what? This plus talks about the resultant of these two vectors. Whenever I want to determine the resultant of two vectors, let us say this is the vector A and this is the vector B. Resultant of two vectors is calculated as what? Start the initial point. Go to the terminal point of a vector A bar. Then from A bar, draw the vector B bar in parallel to it, B bar. Then this is A bar plus B bar. This is actually the resultant of A bar and B bar. Because we discussed it. This is the parallelogram of vectors, we know. That plus is talking about what? The resultant. So the vector from point x1, y1 to another point x2, y2 is x2 minus x1 ax. From that particular point, please see this. I will repeat this. I will go along a line of length mod of x2 minus x1 from x1, x is equal to x1 to x is equal to x2 without changing y. Y is same. Y is y1 on that line. Y is kept constant. X only is changed from x1 to x2. I'll stop there after reaching x2. Then, keeping x constant, I will only change y while moving from y1 to y2, because of which there are two components. One is x2 minus x1 ax, another is y2 minus y1 ay. Vector. Vector from x1, y1 to x2, y2 is x2 minus x1 ax plus y2 minus y1 ay. Listen, this is the good point for us now. Differential vector at any point. Important for calculation. Differential vector at any point is dl bar equal to dx ax plus dy ay. Please remember, Wherever you talk about this differential vector dl bar, for the first time we will be talking about this differential vector dl bar as E bar dot dl bar to talk about potential difference. Next time when you talk about this dl bar, it will be integral h bar dot dl bar to talk about the circulation of the vector. Dl bar, wherever you take, is dx ax plus dy ay. If you are there in Cartesian coordinate system, the dx and dy is never taken as negative. There are cases where you go to the left in x, go down in y. But when you basically talk about this dl bar, ultimately integral limits will tell you from where to where you are going. It is not the minus dx or plus or minus dx or plus or minus dy that gives you in which direction you are going. Differential vector dl bar will always be dx ax plus dy ay. Please remember, if this vector v bar is equal to x2 minus x1 ax plus y2 minus y1 ay, because I know that the distance between these 2 points is x2 minus x1 whole square plus y2 minus y1 whole square under root, modulus of v bar is equal to what? Root of. Now I will write it as x2 minus x1 whole square x component plus y2 minus y1 whole squared y component. Maybe ax small ax plus ay small ay. This is root of ax square plus ay squared. Let us continue this. Mod dl bar is root of dx square plus dy square. Dl bar, wherever you go, is dx ax plus dy ay. Mod dl bar is root of dx square plus dy squared.